the go live button. So
Great.
please continue your story, but now it's live to the
No,
world.
it was just this. There was this book, Tuck Everlasting, that we had to read in like 4th grade or something like that. And it was this family that they would live forever. And I remember, like 4th grade essay, like, would you like to live forever? And I remember very clearly being like, well, like if I live forever, like I would outlive the earth. And then I'm like floating around in space. And then like, what's that going to be like?
Even then.
Yeah.
That's funny.
It's like, man,
That's very deep for a 4th grader.
Yeah, exactly.
Yeah.
Or maybe I was just not a particularly insightful 4th grader.
Yeah.
So in college, I read a story. I think it's called Immortals. It's a story about people that live for so long that their brain just atrophiates and they're not functioning after 100 years or so.
Oh,
I mean, they just get to just lay down and do nothing because they're so bored. So that's what shaped me into thinking that I wouldn't want to live forever.
That's the thing. Like, just saying you're immortal doesn't necessarily mean that you're eternally youthful or like eternally useful even.
If you there's a good have you ever watched the Good Place? Have you watched that to the end? They do a really good job with that. It's sort of dealing with that in the end, just like what if you have eternity? Like, would you even get sick of that? And at some point you just want annihilation.
Do I only have the earth?
No. You have like every possible dimension ever, forever.
Well, then probably not.
Well,
if I have infinite time and infinite dimensions to explore, I probably wouldn't get bored.
Well, and that's what they grapple with. I highly recommend. It's a good show. If you want something that sort of gets pretty deep by the end, definitely watch The Good Place.
I really liked. Do you guys remember Death Becomes Her? Did you ever see this with Goldie Hawn and Meryl Streep?
Oh, wow.
That movie rocks. So good, like because they get eternal life, but then their bodies, like they have to take care of their body. Like if once something is damaged, it's damaged, and that's getting repaired. But they just become this hideous, ghoulish.
I just remember like them seeing through a hole in Goldie Hawn or something.
Yeah, because they're like beating the hell out of each other.
Right.
Shoots her with a shotgun. She just has that giant hole.
Yeah. I was like, I couldn't believe, like, how did they do that?
Yeah. It was really amazing at the time.
Yeah.
Good thing I had dinner already.
I mean,
oh my God.
And we're watching.
It's always my dinner time.
What are we watching right now? We're watching Mayor of Easttown, which is pretty good on HBO. But what was the? Oh yeah, that's right. The movie. There was this movie called Oxygen. It's this French movie. Have you seen this yet? I don't know. It's space related. But it's this woman, or sort of like future related, and it's pretty cool. It's done completely in a hyperbaric chamber, so the main actress is just in a chamber interacting with the outside world. It's pretty great. I liked it a lot.
Do I want to know why she's in a hyperbaric chamber, or will that also put me off dinner?
We'll put you off dinner. You'll get it, but not, or it's not a hyperbaric, like a cryo sleep chamber.
Oh,
wakes up in a cryo sleep chamber, and then doesn't know who she is and tries to figure out what's going on, and running it all from the chamber, which is kind of crazy. So, or like a cryo sleep coffin. So, yeah,
that won't give me nightmares.
It like just small nightmares. But you'll also be intrigued. Okay, we've reached the 5-minute mark, so I guess we need to... Oh, I forgot to say hi to everybody, so let me just do that. I'm a monster. Hi to Bob Moeller, David Dunn, David Fairweather, Frank Tippin, Horizon Brave, Ian Farquharson, Jay Broder, Jim Ashby, Jim Beardsley, John Seffield, Johnny Zed, Larry Beckham, Luke Wilhelm, Nancy Graziano, Paul Patterson, Raj Luthra, Robert Shaw, Sergusi, Tom Garcia, Tom Van Scotter, and I'm just going to say hi to Zapfan because I know you're there. All right, let's get on with this week's episode. I'm going to put you guys all back in your boxes. There we go. I'm going to switch to me. Wait, here I am. Okay. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, June 2nd. It's not June 1st. June 2nd, 2021. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about, is our solar system normal? New Venus missions, delays on Webb, no, and an ancient collision between the Milky Way and a galaxy. Joining me this week on my screen, I've got Alex Teachy. Hey, Alex.
Hey, Fraser. How you doing?
Good. We've got Carolyn Collins-Peterson. Hey, Carolyn.
Hey there, how's it going?
Good. And, of course, last but not least, we got Dr. Kimberly Cartier. Kimberly.
Happy Venus Day.
Happy-
It's Venus Day. I mean, podcast, but Venus.
Yeah, but also podcast. All right. Well, now, before we get into our interview with a special guest, I just want to take a moment and remind you all that you really want to join the Weekly Space Hangout crew. If you like this show, you should be part of the crew. And that's because in 4 weeks, this show goes silent for the summertime. For 2 whole months, we'll be on hiatus, and you will have no more space news coming into your ear. And so you need to collect together with the rest of your friends and fans at the Weekly Space Hangout crew. They will keep you company through the long, hot summer until we come out the other side of this. So go to wshcrew.space, and they will hook you up. And then you can plan what the fall schedule is going to look like. So, all right, let's get on with this week's guest, Dr. Mario Borunda. Mario, welcome to the Weekly Space Hangout.
Hi, Fraser. Thank you for inviting me.
So the question I always like to ask people, who are you? What do you do?
So I'm a physicist. I'm a condensed matter physicist. So what we do is we study how electrons move inside semiconductor, metals, even insulators. So it's not as close to space, except that some of my research is being funded by NASA right now. So we're looking at how to make solar cells that would survive radiation coming from maybe the sun or protons hitting the materials that are used for the solar cells. How could we make solar cells that can survive that and the low temperature that they would be exposed to, let's say, in Jupiter or Saturn?
Right. I mean, people probably don't even realize that much of the development in solar panels came from NASA and this goal to create really compact, powerful, efficient solar panels that could fly to space, because every pound you put in space costs a fortune.
Right, and the lighter it is, the easier it is to put in space.
So you
want to have super thin.
Right. So when I sort of imagine, multiple layers of material sandwiched together, drawing from different parts of the electromagnetic spectrum, but what is the cutting edge of solar panels today?
So the industry standard has been silicon for a long time, but that's for use on Earth. Now, if you put if it gets exposed to any radiation, the silicon goes bad. And that's because the crystal structure changes when protons pass by and hit it. Now, if we have another material, there's a couple of exciting materials right now. One of them is called halide perovskites. Mm-hmm. And what perovskite is just the structure that the atomic structure that this has, this crystal. So these halide perovskites have a 25% efficiency. That's the world record that they have right now. It's below the most expensive ones that are in use right now by both the military and NASA. But if you look at it, they're so much cheaper to make. And the most important thing is that the super expensive ones go bad as soon as they get exposed to radiation.
Right.
These perovskites don't go bad. Actually, they even heal themselves and become better if you expose them to radiation. We have evidence of that.
But don't the perovskites go bad when they reach air?
Yeah, that's the only issue that they have right now. And that's why we're looking at them, at the mechanism that happens when you expose them to oxygen, when you expose them to water, they start to degrade.
Yeah.
So what you do is that you make one and then you encapsulate it and don't let the air get near it.
But space, there's, no one can hear you scream, but also there's no oxygen in space. And so it's like
and
the perfect
humidity.
place. Yeah. I did some research into this at one point for a video we were doing, that you could just like spray this stuff onto surfaces in space and create enormous, highly efficient solar panels that get better with radiation. It really feels like the perfect tech.
Yeah.
Yeah, and we could spend a whole episode talking about this, but the reason you sort of came across Nancy's desk, I'm sure, is that you recently reported on the latest state of warp drives.
Exactly.
When do we get a warp drive?
Hopefully this century.
Okay, wow, all right, I'm in.
But the main issue is how to build it, right? But we have theorists are coming up with better ways and better approaches towards making them possible. So that was what the write-up was about.
So what is we've obviously been poorly educated by Star Trek and Star Wars and things like that about what a faster than light system might be. What would an actual practical warp drive function like according to the laws of physics as we hope we understand them?
So there's several ideas, right? Like, for instance, if we're thinking about Interstellar, Thor, Stargate, what they're using is wormholes. So in a wormhole, you have that the fabric of a space-time is concentrated so much that you could kind of travel from this portion of space to this other end in space, because the space gets compact so much that you could join the two together. So that's one of the ideas that had been around for a while. The other one is this warp drive, which is what is used in Star Trek. So for the warp drive, what you have to think about is, like, you have a space-time that could be seen as a flat thing. When you have something massive, it curves the space-time down. So now imagine that you had a way to make the space-time. So mass, something heavy, makes the space-time stretch out. So that's how we experience that as gravity. Now, the idea of the warp drive is that instead of just stretching a space-time like gravity does, like a black hole would do, or the sun or our planet, is to think about it that it can stretch in this direction, but you're traveling in that direction, and you would compact in this direction. And that was something that was come up by Dr. Alcubierre, Miguel Alcubierre, when he was looking at, is it mathematically possible to get a solution that can do that? So we know from his work that it is mathematically possible. And what he did is that he kind of reverse engineer. He put the math in and says, this is going to break the general relativity laws. The reason for doing that is that there's no way to go the opposite way where you find the solution, but he actually had the solution he wanted. He fed it to it and then got a way to do it.
Right. And if I understand, the trick was you had to come up with, I think, was it negative mass? Was that
right?
So you had to create something which there's no evidence exists.
Yes, exactly. So there's no evidence that negative mass exists. So what we have then is that you can make the distribution of energy around something to emulate this negative mass.
Huh.
So negative mass, there's no way to figure out if it exists or not. We never observe it. Exotic things like this we haven't seen yet, so let's assume it doesn't exist. But then if you have a lot of energy and you distribute it in a particular way, you actually can get a negative distribution of the energy density. So one approach, this is something that has been looked by NASA, and I think is the approach that probably is going to get us there. If you have two plates in space, two metallic plates, you have actually, due to quantum mechanics, that electrons and positrons come out of the nothing, of the vacuum, exist for a little bit, and then they contract onto each other. And these fluctuations in space happen, right? So now if you have two plates, what happens is that inside the plates, there's only this much space for those fluctuations to happen, and you reduce the amount of fluctuations because they have to fit here. But on the other end, which is all the way across the universe, there's more. So now that's a negative energy density in here, in this space between the two plates, versus the one on the outside.
And this is the Casimir effect, right?
Casimir effect.
Yeah,
right.
And so you end up with a force on the plates because
attraction. Because
essentially the wavelengths of the particles that are appearing in the universe, they're not able to fit inside those plates, and so you get that force. So
Right.
and so I'm sort of envisioning then there's like some kind of because E equals mc squared. If you don't have mass, you can just substitute just a whole bunch of energy, and in this case,
Exactly.
you can put energy into the kind of configuration that you need to reach the equivalent of negative mass.
Right. And
Right.
this means that you have an imbalance between particles and antiparticles that you're creating here, electron, anti-electrons. And if you make it right, this negative energy density would curve the space-time around and maybe make a bubble that is the size of the spaceship that you would go into.
Now, as I understand, one of the other challenges was that the math suggested that you might need as much energy as is available in the observable universe to turn on your warp drive. So has there been some kind of breakthrough on that front?
Yes. So that was the original Alcubierre's warp drive. He needed all that mass to create the negative energy distribution. So that was in 94, 95 that he was proposing this. But then by 99, there's another physicist, Van den Broek, who showed that you can make the surface area constant, but expand the volume inside the bubble. So kind of like stretching this bubble of a space-time that you would put the spaceship in. And that would reduce the energy requirements. So keeping the surface area constant, but then reducing the thickness of the bubble.
Right.
Once that happens, you only require the mass of maybe the sun or Jupiter, according to his estimates.
The mass energy equivalent or the
Right.
you
So I
only
guess
have
you had to turn in Jupiter, all of that mass of Jupiter, turn it into energy.
Oh, well, that's downright affordable. Then sure.
It's still not practical, though, right?
Right.
Not
Is that
for
the
us.
best we can do, or has someone got an even better idea?
And that's what these two recent papers came out in the last year or so. One is by Alexei Bobrick and Gianni Martyr, and another one is by Eric Lenz. So these two papers were published recently, and what they do in the first paper, the one by Bobrick and Martyr, is that they're modifying the space-time within the bubble in such a way that they don't need to use negative energy. So now their solution is a little bit not particular to the warp drive, but what they're realizing is that their warp drive cannot go faster than the speed of light. But what they're saying is that we can change the space-time around an area and make things go either really slow or really fast. So that's what the research has implications for. Maybe you can put something in there and make it grow super fast because the space-time gets modified inside of their bubble that doesn't need negative energy. Or you could put yourself in the bubble and age really slowly as you travel across.
Right. It's almost like the sublight speeds. So, I mean, it's sort of like this idea of you traveling at relativistic speeds and for a human lifetime while the rest of the universe ages millions or billions of years. I mean, this is
Exactly.
right. Not your problem, but, you get a chance to travel to Andromeda. So I guess what would that journey feel like if you hopped in your spaceship and you turned on this warp bubble and began your trip? What would you experience?
I guess you would see this horizon around yourself, and it would be hard for you. You wouldn't be able to experience that time is going super fast around you because you can only see inside because you're covered by this bubble.
Right.
So then you would be going at your own particular time, whereas the people outside, the universe is going outside at a super fast pace compared to you. But because of that imbalance, you wouldn't be able to see. You have like an event horizon around you.
And so you would still be traveling like imagine I wanted to fly to, say, Alpha Centauri.
Right.
So what kind of time would I experience in my journey?
I guess you can tune your time to be whatever you wanted, basically.
Right. So I can
and then
get
you
to,
can just
so I
travel
can get to
across.
Alpha, right. Okay. So I can get to Alpha Centauri in a minute, but 4.5 years would have elapsed. For the,
maybe even more, because you're not really traveling at the speed of light. That would take a while for you to accelerate towards the speed of light and then decelerate. But yeah,
And
maybe it takes 10 years for your travel, right?
And what about the energy use? Are we down from turning Jupiter, grinding up Jupiter and turning it into warp drive fuel?
Right, because this one used according to their calculations, they would not need to have a negative energy field around your bubble. So that's one approach. The other one is by Eric Lenz. And he also says, I have found a solution that does not require the negative energy. What he's doing different is that he has a different geometry approach. So when we look at the equations for general relativity, we're looking at geometry that is kind of parabolic or elliptical, right? So if you take a cone, if you cut the cone through some axis, you can see an ellipse or a circle or a parabola. If you cut it like this, or like this. So what he did is that he went and looked at solving the equations of general relativity, but in a hyperbolic geometry.
Whoa.
So that was the main thing that he changed. Instead of being in a parabolic, a parabola that looks like this, the one that we know from, he instead is cutting like this and making a hyperbola. And when he's solving it like that, he finds out that this geometric approach, the warp drive, the equations to solve to make the warp drive possible wouldn't need to use any negative energy. And in his solution, then his solution can get to travel faster than the speed of light, because it's basically the same as Alcubierre's idea that you would be able to compress a space-time in front of you and be able to get there faster.
So as a physicist, which of these techniques do you find more satisfying?
Well, I think that for me, the warp drive would be that you could travel faster than the speed of light would be the most interesting one.
Sure, but when you look at the math and think about the possibilities, again, which one do you think is more feasible?
Yeah, if we're comparing warp drives to, let's say, wormholes, right? I don't know if you prefer wormholes or not.
I do. Yeah, I want to Stargate all day, every day. Yeah.
So I guess for the wormhole, we have to figure out one problem. One big problem is that if you were to get close to a black hole, you're going to get stretched so fast that you're going to turn into spaghetti so fast that you're not going to survive. If we could fix that, and actually there's research, another, not related to warp drives, but in this case to wormholes, there's research, and it makes a lot of sense now that somebody has thought about it, right? It's like obvious. One solution is gravity, which is what would pull you apart as you get close to the black hole, could be compensated by making the black hole be a particular charge. So if I start throwing protons at the black hole, it's supposed to be charged positively. Mm-hmm. So now let's say I have myself positive charge too. Somehow I wrap myself in the carpet, get all electrostatic-y. If that too, I have gravity pulling on me super hard, but then I also have electromagnetic forces, positive, repel each other, and they could balance themselves out. That might be a good way to get across through a black hole and go from this side of the galaxy to the other, if wormholes work.
So place your bets. When does, this is a good nerdy Star Trek reference, when does Zefram Cochrane fire up the first warp drive and meet the Vulcans? How long do you think it'll take for us to be able to turn this into some kind of practical technology?
I think that well, we have these mathematical models, right, and ideas like this, but I think that I would hope that it's in the next 80 years, so that it could be in this century or maybe the next one.
Yeah, that'd be great.
And having the experimental proof, though, is really, really the thing that we need. If we don't have an experimental proof, it's going to be super tough. We could do all the math that we want, right? But the proof is getting an experiment to work.
Yeah, exactly. Well, it's awesome. Now, you wrote a great article on the conversation and other places, and so I know we'll have a link in the show notes. But if people want to follow your work and learn more about what you're doing, where should they go?
So they can go to Borunda, that's my last name, OKState.edu. I'm a professor at Oklahoma State University, and that's my website.
Perfect. Well, thank you so much for taking the time. Will you come back when they do actually fire up a working warp drive and let us know how it's going?
If I'm alive,
yeah,
I will.
Awesome. All right. Well, thank you so much for taking the time to chat with us today, and good luck. Good luck getting perovskite crystals operating in space. That's the practical technology that I'm super excited about. So, thank you.
Thank you.
Bye-bye. All right, let's move on to the news of the week. Kimberly, give us the big news.
Venus!
Yes.
Sorry, that was me screaming into the microphone. Apologies to people who had their volume up really loud.
Give us. So what was announced? Give us the
context.
History.
Context. Earlier today, June 2nd, NASA announced that it picked 2 Discovery class missions for the next round of Discovery class missions. And they are both traveling to Venus, which is extremely exciting because it's been all about Mars and the moon for many, many decades. And Jupiter and Saturn were in there too. They did great stuff. But NASA has not been back to Venus since 1978? Question mark. This is why I wrote notes down.
Well, I mean, the Parker Solar Probe took some nice pictures.
NASA has not had a sustained presence at Venus since the late 70s.
80. I don't know this down. Magellan was the last.
Magellan ended in 1994.
Yeah.
This is right. U.S. has not visited the atmosphere of Venus since the late 70s. Slightly after that was the last time the Soviet Union visited Venus's atmosphere, which was Vega 2 in 1985. It's been many decades. I was not alive during either of those missions. And I was only slightly bored, like I was really, really young at the end of Magellan.
Now I'm feeling old.
I'm dating myself.
I was in high
school. The point is that NASA has not studied Venus for a while. We, humanity, have not traveled through Venus's atmosphere for a very long time. And since the end of sort of like the big push to explore Venus back in the 70s and 80s, there have only been a handful of missions that have had a sustained presence studying the planet that's closest to us and most similar to us in terms of its size and mass and things like that. Which is why it's very exciting that NASA is sending 2 Discovery-class missions. One is an orbiter, which is the Veritas mission, which has a very long acronym that actually pretty well describes what it's going to be doing.
But
it
a
is
backronym.
Going to be, it's a backronym, yeah. Venus emissivity, so that's the E. In Veritas, it's going to look at the infrared emissions or heat coming from the entirety of Venus's surface, making a map. Radio science, which is very important to understanding a lot of the atmospheric processes, as well as volcanism and possibly lightning. There's going to be INSAR, which is synthetic aperture radar, to get us a 3D topographic map of the surface, which is what the T in Veritas is.
That's cool.
A full global 3D topographical map of Venus, which we do not have right now.
We have a terrible one. So
a terrible one.
Yeah, the one from Magellan.
But this is going to be high res.
Yeah, the one from Magellan is like 100-meter scale pixels.
This is going to be much, much finer scale.
Yeah.
Technology has INSAR technology has advanced quite a bit since the last time we've done this. And then also spectroscopy. That's the S part of Veritas. And this is going to be an orbiter mission. And the not orbiter part that I'm really excited for is Da Vinci. If I have to pick, I think I'm more excited for Da Vinci because it's an atmospheric probe that's going to go through the atmosphere of Venus to get a full vertical profile from the top to the bottom of all of the atmospheric chemistry going on, taking very detailed, precise measurements of the chemistry of Venus's atmosphere, and then also getting a look at sort of like the giant, like continent-sized puzzle pieces that make up Venus's surface. They're not quite tectonic plates because they don't move, but they are what could have been at one point tectonic plates, but no longer are.
So,
and we don't know why.
Is this a suicide dive, or is it going to be able to stick around in the atmosphere?
It's kind of a suicide dive. Anything that goes down onto the surface is going to die at some point.
In about 1 hour, if it's built like a tank.
Maybe. I have notes on that.
Okay.
But the point it's not going to be like a balloon platform or an aerial platform or something like that to have a sustained presence in the atmosphere. It's really just going to drop down onto the surface and continue to take measurements that way. It might last more than a couple hours. I think the current record holder on Venus's surface is something like a little over 2 hours from one of the Venera probes. I don't remember which number, 13 or 14 or something like that. There have been a lot of experiments going on at NASA Glenn in their Venus simulation chamber to test out new advanced technologies to see what will work best on Venus's surface and try and push the boundary of how long something can last. So NASA has been testing technology to last longer on the Venus's surface for a while now. So that's really exciting.
So today's announcement is great. 2 Venus missions. Yes. Obviously, they're going to go together, I'm assuming, in one.
They're both sort of scheduled for, they're estimating they're both going to be ready about 2028 to 2030. I can only imagine it would be most efficient to send them at the same time. Plus, given that one's an orbiter and one's an atmospheric thing, they will probably work best in conjunction with each other.
But by being excited for 2 missions to Venus, you also have to be sad, or you're a monster.
I'm a little bit sad. I'm not a monster.
Right.
Anyone who knows me, who knows me knows how much I love the ice giants.
Yes.
Knows how much I love the moons of Jupiter.
Yeah, Io.
Of course, I am devastated that we're not going to be studying the most actively volcanic place in the solar system, which is Jupiter's moon Io. The Ivo mission was like spectacular. I was really excited for that proposal. And literally anything that could go to an ice giant, I want. So I was very sad that Trident did not make it for this round, but both teams have already said that they're planning for the next round of Discovery missions. The ice giant launch window is not yet closed for a Discovery mission. By that, I mean, to get to the ice giants and with any sort of efficiency, we have to launch like mid-2030s. So we're closing in on when the very latest we can choose an ice giant mission, but we're not yet past that limit.
Yeah.
So of course I'm sad that we're not going to Io or to Triton. But at the same time, Venus. Okay. A planet that we just don't understand, that we really need to in order to basically answer any questions about Earth. Why we are the way we are and why it is not.
Yeah, I have a million questions about Venus. And
everyone does, because we haven't been there in a while.
Yeah. And
anyway, very exciting.
And there is a deadline because I've expressed on many occasions that I intend to push Venus into the sun. So
Hey now.
It's awful. It's just terrible.
Why?
It's just the worst place. So
no, it's cool.
So
not cool. It's hot. It's
hot.
Like really hot.
Yeah.
But,
hot enough to melt lead. Hot enough to crush and destroy any rover that goes down there. So anyway,
that's pretty epic.
It's evil, is what I'm saying.
Kind of badass.
An evil planet, and All right, maybe we'll wait until after it gets studied. That's fine.
Thanks. Thank you, please.
I'm definitely excited about the Da Vinci mission, but NASA does have some pretty great ideas for actually sticking around in the atmosphere and examining it for longer periods of time. And so I would really love to see some kind of longer term atmospheric exploration. So
oh yeah, for sure. There are plenty of plans. I think you're probably talking about like a sustained aerial platform or a balloon.
Yeah,
or something like
that.
Like
balloons that can change altitude and
very variable altitude balloons.
Yeah.
Yes, and there are, for example, the oft talked about and not much funded Venus flagship mission does have a sustained balloon component.
Yeah.
Which would be very cool.
These are just Discovery class, right?
Yeah.
mean, these are
The
cheap.
current ones that were selected are Discovery class, which means they're about $500 million and a pretty short like build to launch timescale. Not anything like James Webb. But a Venus flagship would be a longer term mission. It would have multiple components that would all work together to get a full comprehensive look at Venus. The problem is we just don't know enough about Venus in order to make a longer term mission viable. It'd be way too risky to put all that time and money and effort into a Venus flagship until we actually know what happens on Venus.
I would have gone for Trident and Veritas, I think. That would have been my call, but...
I mean, probably mine too, but I don't make these calls.
That's fine. Neither do I. Apparently our votes don't count. Okay, you mentioned James Webb, so why don't you let's hit us with the news so we can all just grieve together.
Is anyone surprised that there's another delay in James Webb? Is anyone?
What?
Have I ever come on this show talking about delays or overfunding in James Webb?
Possibly.
I don't. Yeah. Has that happened in the past? I don't know.
So what's the news?
James Webb is not going to make its Halloween October 31st launch date, which was decided sometime last summer, and they've been working really hard to get to it. But it's just not going to happen because of a couple of logistical and technology things that they have been working out. The good news is that the launch date is probably only going to slip by a couple weeks. They're estimating like mid-November to early December. So it's only like 2-3 weeks of a delay, which is not bad compared to past delays. That's my caveat, compared to past delays.
And this is purely being extra cautious about the Ariane 5
being super extra cautious
rocket.
Yeah, the issue is that the Ariane 5 rocket, which is going to launch James Webb up into space, there have been some payload fairing issues that they've been working out. It's been diagnosed. They have are currently like finishing the fix for it. They're going to do 2 test launches with the fixed fairing to make sure that it works before they put Webb inside and launch it up into space. Yeah. They're being super extra cautious, which I'm kind of okay with.
Yeah.
Like, I would prefer that they are extra, like if there's a hint of something going wrong at this point, I would prefer to wait like an extra week or 2 and just have it go right.
Yeah, I'm totally fine with it.
Yeah.
But you had a shred of good news, right?
I did.
I thought you did. I thought you said you had some good and bad news.
Venus was my good news.
Oh, Venus see. You had no news. James Webb good news. Okay.
No.
All right.
I mean,
it's delayed, but not that bad.
The telescope is fine.
Yeah.
There's no issues with the telescope. They're going to fold it up in the next couple weeks. The final fold, I'm putting it in a shipping container. I've learned that they're keeping the travel plans to get Webb from the U.S. to French Guiana under like super wraps because it's traveling by sea and they're worried about pirates.
Yeah.
Which is a legitimate issue still in today. It's not just like relegated to Disney movies. It's like an actual piracy is a real issue.
Shouldn't they just send an aircraft carrier? Isn't like that what these things are for, is to protect science?
I don't want to put Webb up in the air except the once.
No, like to have an aircraft carrier just go with it to protect it from pirates.
A destroyer or something.
Yeah. Send a military fleet is what I'm saying.
I also don't make those decisions.
Yeah, all right.
I would do that.
Yeah, that's all I'm saying.
I'm also not in charge.
Yeah.
So slight delay in Webb. They're not going to make their really clever PR Halloween date. Sorry.
Yeah.
But the telescope's fine.
All right. Well, you bring both good and bad news. Yeah, you giveth and you taketh away. All right, Carolyn, what news do you have for us?
Ooh, what news do I have? Well, I've been following a story about galaxy collisions in the Milky Way, which is not a new story, but it's about a collision that happened about, I think, 10 billion years ago between the Milky Way and a former dwarf galaxy with a really cute name called Gaia Enceladus Sausage, which you guys all had a laugh about. And the sausage part comes from, if you map the distribution of stars in velocity space, it has this kind of sausage shape. So they called it that. So people have been looking at this for a while, and so the latest story has been that a group of astronomers at Ohio State have used a combination of methods to study the stars, that basically resulted from this. And part of the reason for that is, we've known about collisions for a long time. We have great pictures of them. You can look at the antennae. You can see great pictures from outside. But in the Milky Way, we can't see outside to see what kind of effect ancient collisions had with the Milky Way. So we kind of have to do like they did in CSI Las Vegas. You let the evidence tell the story. And in the case of this story, it's about the stellar characteristics. And so this group of astronomers at OSU started looking at characteristics of stars in the galaxy using the spectroscopic apogee survey, which is probing the evolution of the Milky Way. Science called astrochronometry and astroseismology. It's a great name.
Yeah.
So it's basically determining the ages of stars using astroseismology, which basically looks inside of stars, tracking interior oscillations to get a really good idea of the dates or the ages of these stars. So if you know what to look for when you're looking at stellar populations, you can tell different populations of stars, not just by their age, but also by their metallicity and a little bit about their velocity, where the directions they're heading, their motions through space. And in this survey, they found a couple of different populations of stars, some that were original to the Milky Way that include a group of kind of older red stars. And so they were probably in the original Milky Way dwarf that existed about 10 to 12 billion years ago. And then they found these other kind of alien stars that don't really match the metallicity of the quote, or original stars, and their motions are a little bit different. And so from all of this, they have determined that this Gaia Enceladus sausage early Milky Way collision took place, and it changed the shape of the thin disk in our galaxy, kind of puffing it up to a thick disk. And it also changed the distribution of stars. So a lot of the original stars are in the thick disk, but a lot of the newer stars that came from Gaia Enceladus sausage, we had to just call it GES, are now distributed out in the outer halo.
Just the sausage is...
Yeah, the sausage.
I mean, if they're going to call
and
and that's just going to drive some astronomers bonkers. I get to see Alex steaming.
Well,
right now.
I kind of wish they'd kind of simplify that, but so it did have some definite effects as these galaxy collisions do. There was a wave of star formation that took place, influx of metal-rich stars, and we gained about 8 to 10 globular clusters out of it as well.
Very cool. Now, I had read, and I don't know if this is related, that sort of, the Milky Way's disk is warped and it has all of these interesting features that it's gobbled up of other galaxies. But the thinking is now there wasn't any cataclysmic event that happened in the history of the Milky Way, that it really was built up through a series of smaller mergers of dwarf galaxies, but nothing really dramatic. Nothing like what's coming. No, I mean,
it's probably a combo of all that. But then you also have this upcoming, and I don't know that we're feeling the effects of Andromeda coming close, but that would definitely warp it in the future. But yeah, there isn't really any evidence of some giant explosions and things like that.
Yeah, the halos of Andromeda and the Milky Way are already starting to overlap, even though we're still. Oh yeah,
the dark matter halos. Yeah, that was another thing that the Gaia Enceladus sausage brought was more dark matter as well. So it looks like a lot of subtle changes. It's not like one giant clash of the titans, like we all kind of thought in the beginning. Although then you look at something like the antennae and you wonder, are we going to look like that in a few billion years?
Yeah.
So yeah.
Yeah, I mean it's going to get a little weird. We're going to get furious star
formation. Or then there's that Andromeda collision, that we're all kind of waiting for too. So
yeah. Will the Milky Way's supermassive black hole turn into a quasar again, etc. So interesting.
Super a lot of speculation. Yeah.
All right. Thank you, Carolyn. Alex, what do you got for us?
Yeah. So this has been a story in the last week on the exoplanet front for not entirely all good reasons. So we'll get to that. But what I've been sort of interested in is these latest results from the California Legacy Survey. It's a pair of papers came out in this past week looking at the demographics of exoplanetary systems, specifically these gas giants, ice giants in the outer reaches of these exoplanetary systems. So, our solar system, we have these inner rocky planets, and then farther out we have the gas giants, Jupiter, Saturn, Uranus, and Neptune. And it's been an open question, of course, how common or how uncommon are we? That's a question that I always am kind of coming back to. What ways are we?
Are we normal?
Normal and not normal,
right?
And so this is an open question, specifically with these gas giants farther out from the star, because they're very difficult to detect, regardless of whether you're trying to use the transit method or the radial velocity method. We just have observational biases that are keeping us from really seeing these planets in large numbers, and so we don't see them in large numbers. And the question is that a real effect, or is that just an observational bias? My sense has always been that it's been a bias, but people that are, really much more into the exoplanetary demographics than I am, they've said that no, really, actually, there's really not that many. So here comes this brand new set of papers from California Legacy Survey. They've been using radial velocities, and they have data going back 30 years. In a lot of cases, they've looked at 700 some stars, and something like 115 or so planets, including 14 new ones.
Sorry. So hold on 1 second. Have we been using the radial velocity method to search for planets for 30 years now?
Yeah, I guess
PEG
this
51b,
technique,
1995.
it's a matter of sensitivity, right? So 85, 1990 or so.
1995. It was 95, and so it feels okay. Anyway,
and so you can look at binary stars before. It's always a matter of sense to how deep can we go. And they've been looking at all these stars, and actually there's been some incredible cases where it's a flat line for years and years and years, and then this is a very eccentric planet, so all of a sudden they get this big signal, and they find these planets that are, in some cases, you don't even have to see the entire orbit in order to find these planets at very long periods. Over the last year or two, they announced a planet with a very long orbital period, just based on this super old data. So it's really cool that we can now sort of probe these greater distances, and it's just about patience, right? It's just about how long you're willing to look at these stars and keep visiting the same stars to find these very long period planets. And so the answer seems to be that if you're going to find these gas giants, they're going to be preferentially found in the vicinity between 1 and 10 astronomical units, which of course is where we find Jupiter and Saturn. That's also really exciting, because we'd also not want these planets to be super far flung, right? If you see these protoplanetary disks or these direct imaging, a lot of times we've seen these things at 100 AU or even farther than that, and that would be extremely difficult to study those planets. So if they're in the 1 to 10 AU range, that's really kind of potentially probable on a human life scale. So that's the good news. On the other hand, they're only finding something like 15% of stars are going to have planets like this. And you can slice it up all the ways you want about stellar metallicity or the spectral type, what kind of star it is, all these sorts of things. And so they investigate all of those things with the demographics. So short answer is, if we're going to find these gas giants, 1 to 10 AU is basically where you should expect to find most of them. The hot Jupiters notwithstanding. But on the other hand, we are a little bit unusual when you start to look at that 15% number. Now, the other reason that this has been sort of, unfortunately, on the minds of astronomers is because these papers have 30 some authors or some, and one of these authors was excommunicated from the field 5 years ago. Very famous astronomer, especially in exoplanetary science, but for serial sexual harassment was sort of thrown out of the field. Well, he contributed to a lot of this work that is going back decades, and so he was added as an author on these papers, or he was listed as an author on these papers. And if you follow astronomers on Twitter, you probably know that everybody has been real up in arms about this. And a lot of people feel one way. There's some people that feel a different way about it, and so it's been a real controversy here, and it's raising very tough questions for the field about what do we do with these kind of folks. It's not restricted to science, of course. We look at problematic directors or actors, people that have done bad things in their past, are we allowed to watch their movies, or are we allowed to say, oh yeah, he's a good director and that sort of thing? And in this case, just the appearance of this name on these papers is really very bothersome to a lot of people. So astronomy is really wrestling with this issue right now.
It is. It's definitely troubling, but it's also good for people to just have it not feel like it's been flushed from the system. And now, the Me Too movement, it's moved, astronomy doesn't have to deal with this problem anymore. I mean, there are repercussions that are going to last for decades. When you think about all of the people whose careers just weren't able to proceed because of the abuse that they were receiving, right. like there are people who would be astronomers today who aren't because of what they experienced. And so I think this is a deep systemic situation that's going to have to be worked through, and it's going to take probably decades more to get to the bottom of this and for us to deal with this. And hopefully we can continue having not we, I'm not an astronomer, but you and the rest of your colleagues can have good conversations and get to the bottom of a way to deal with this into the future. And these situations are going to keep coming up.
Painful conversations, obviously, but they're going to keep happening. Yeah. And we have to keep wrestling with it, right? It's not one and done.
It's
right?
not
we have to
solved.
Exactly right.
Yeah, absolutely. So, anytime you talk about exoplanets, I want to bring this back to your specific field, which is just the fact that, if they are finding, the number of planets, the like Jupiter, like Saturn, does this give any hope for the finding of the exomoons?
Yeah, well, this is where we always, we tend to think, and the evidence is mounting, but it's still, not great evidence. But we tend to think that, as you are, I think, alluding, that these gas giant planets are in general going to be the best places to look for exomoons. And so that's why I really want them to be at the 1 to 10 AU range rather than, 30, 40, 50 AU. This is a range where we could conceivably actually find these exomoons. So yeah, I'm excited for that reason. Definitely.
Yeah. I mean, it's really interesting, though, just to think about the kinds of observations that it takes to spot a planet, and then you have to keep observing that planet, waiting 10 years for that planet to show back up. What are I guess, like, the amount of the radial velocity, what kind of speeds is the star moving at to make those kinds of detections for something that's so far away?
It's a good question. I think something like Jupiter is, I'm not a RV guy, but somewhere in the 1 to 10 meter per second range. Right. And our current limitations for radial velocity, state of the art, is about 1 meter per second. Okay. That's amazing. I mean, that's, walking speed, looking at a star that's hundreds of light years away, and we're seeing it walk away from us.
Yeah. But Earth really is like in the 10 centimeter
10
range,
centimeter.
Right?
Yeah, exactly right. So I think Jupiter, it's a mass issue and it's a lever arm issue and that kind of thing. So we can really see these things. It's a matter of having the baseline to really get the detectable signal.
So not to put you on the spot then. So then a Ganymede affecting a Jupiter that's affecting a star. Now are we in the millimeter range?
Oh, you'll never see an RV signature from the moon.
What do you mean never? You can't say never. You literally just plot it.
Farther orders of magnitude.
Just plot it on an exponential graph. You can predict the date on when you'll find it.
Now,
just start writing your paper now.
No. See, here's the problem. This is what we're interfacing with. There's stellar noise. There's noise on the surface of the stars that is a systematic that you just can't really get below. So when we're talking into these really, really small RV signals, the stellar surface activity is just going to totally wash it out. So it's not even a matter of technology at that point, unfortunately. So what's really exciting is that, eventually with direct imaging, the expectation is that we will be able to measure radial velocities of the planet, not the radial velocity of the star,
right.
But see the reflex motion of the planet itself with the moon. That's really going to be, sort of the more promising avenue, I think.
Awesome. All right. Well, we've reached the end of our show. I will summon everybody back in. Actually, you know what? First, well, Alex, you're the one who's still on my screen. So why don't you tell us what you're working on and where people can find out more?
Working on exomoons all the time, but also more recently looking at trying to go after some of these long period planets, specifically with the test data. I'm sort of excited to get my feet wet with that. So
it feels like an undiscovered space because it's such long times. It's pretty exciting.
Yeah, I mean, TESS is an enormous data set,
Yeah.
and there's a lot to go through. It's a real big data problem, and so
Awesome.
so I'm excited to dive in there. And if people want to follow me, they can follow me on Twitter at AlexTici.
Perfect. All right, Kimberly.
Hey, people can find out what I'm doing on Twitter at AstroKimCartier and at eos.org, which is where I publish all my stuff. I've recently been talking to all sorts of people who are going to use James Webb to study exoplanets to figure out what they're looking at and why, and what they think about the upcoming slate of observations. So that should be coming out in a couple weeks.
Very cool. Carolyn.
You can find me at SpaceWriter on Twitter and thespacewriter.com on the web. And I am just finishing up work on our documentary about exoplanets.
Oh, so cool. Where will
Been
people
working
be
on it
able to
for
see it?
Planets for everyone.
Yeah. It's a
It's a
theme.
full dome show for planetariums.
That's awesome.
Yeah.
Yeah, for people who don't know, Carolyn writes and produces planetarium shows, among the
Among
thousand
other
other
things,
things
yeah,
that she
yeah.
does. Yeah, that's amazing. And if people want to follow your work,
At SpaceWriter and thespacewriter.com.
awesome. All right. Now, I'm going to bring us all back. I don't have anything super interesting that I did another question show. I've got an upcoming interview. I'll get into the details in a future thing. I don't have them in front of me, but a new technique for equipment that could detect life, miniaturized, could fly on any spacecraft, and also not just life as we know it, but life as we don't understand it through sort of chemical imbalances in the environment. So anyway, talking to the researchers that are doing that. Yeah. Thank you, everybody, for watching us this week, both on YouTube and on Twitch if you're out there. Thanks to all of the moderators, and a special thanks, as always, to Nancy Graziano for organizing everything that we do. Reminder, wshcrew.space. Join the crew. They'll keep you entertained over the summer hiatus. All right. Thanks, everyone, and we will see all of you next week. Yay.
So long.
Find the button. There it is.